Hey kids, let's do some more work with our derivative tests. Notice in this example, they are asking me to use the first and second derivative to graph f. So my goal over here is to get a graph of f. Well, didn't they give me f? No, they didn't. Look at, read. This is the derivative. They're giving you the first derivative. I don't see the graph of f. So I'm only going to be able to get an approximate graph of f, but I'm going to do a pretty good job, as long as I recognize that I have the first derivative here. Be careful. It's not only important that you label, it's important that you read the labels given to you. So now remember, a wrap-up. What have we done so far with first derivative tests and second derivative test? The first derivative test, remember, is for extrema and increasing and decreasing intervals. And my second derivative test is for poi and concave up and concave down intervals. Now, look at your equation for your first derivative. It's cubic. There are no endpoints on the first derivative. And if your first derivative is cubic, what did it come from, right? What can you take a derivative of and end up with something x cubed, right? It's some kind of x to the fourth. Right? I don't know how many terms or whatever it has. Don't know. But it's some kind of x to the fourth, right? So pretend I started with something x to the fourth and I wanted you to tell me using calculus where the maxes and mins were. You would take the first derivative and set it equal to 0. So determine where the derivative is equal to 0 or does not exist. And again, you wouldn't be worrying about endpoints. You know this comes from a fourth degree function. Fourth degree has, right, an infinite domain. So where is the first derivative equal to 0 or does not exist? Write down the first derivative. Factor it. Make your suspects, put them on a list, put them on the lineup. Use your labels on your lineup. Notice I have arrows because I have an infinite domain. I don't care whether you put the labels on the left or the right of the number line, doesn't matter. I just put them over here because I had bullets here. So f prime of x, the derivative is 0 when x is equal to 0 and x is equal to 3. Now I'm going to test values on this interval, right? 4x cubed. So I'm going to test a number below 0. This factor is always positive. Put a number in below 0 here. -1 minus 3 is negative. Put a number in between 0 and 3, like 1. This factor is always positive. 1 minus 3 is negative. A positive times a negative is still negative. Put a number in past 3. The first factor is positive. The second factor is also positive, and a positive times a positive is a positive. A fourth degree polynomial is continuous, and if a continuous function changes from decreasing to decreasing, there is no extrema there. The derivative did not change sign. You have a horizontal tangent, but the derivative did not change sign there. However, the derivative did change sign around 3. So your derivative was negative, your original was decreasing. After 3, you had a horizontal tangent at x equals 3. Then your derivative was positive, meaning your original was increasing. This is a continuous function. If you change from decreasing to increasing, you must have passed through a local min. And that is your only candidate. And by the way, now that I know that I have x to the fourth, the local min is going to end up being my absolute, right? So let's go on to our second derivative. What is the second derivative? And set it equal to 0. The two x's that make the second derivative equal to 0 are 0 and 2. Notice my number line here is labeled, again, with arrows because I don't have any endpoints to consider. And the second derivative is doing what on these intervals? Now, this derivative is a parabola that opens up. I don't really have to test any values, right? A parabola that opens up with 2 x-intercept is the range is positive, negative in between the x-intercepts, and positive after. When your second derivative is positive, by the second derivative test, your function is concave up. When your second derivative is negative, your original function is concave down. When your second derivative is positive, your original must be concave up again. And if you are a continuous function with both, which all of these, the original, fourth degree, third degree, second degree, all are. Fourth degree is continuous, and if you change from concave up to concave down, you must have passed through a point of inflection. If you change from concave down to concave up, you must have passed through a point of inflection. So that's all the mechanics of the first and second derivative test, right, for extrema. And I also see my increasing and decreasing intervals. I see I have 2 poise, and I have concave up and concave down intervals. Now let's draw. So here's what I do. I make a vertical line on my graph through 0, 2, you know what, I think I might make this 1 and this 2 maybe, just to spread out my scale, and then at 3. One, 2, 3. Okay. Now, what am I going to do? So, from negative infinity to 0, I am going to decrease. And at the same time, from negative infinity to 0, I'm going to be concave down. So concave up. Decrease and concave up. All the way to 0. Again, I don't know exactly where I hit there, but so it doesn't really matter what height you're at. I am decreasing and concave up because that's what my derivative test said to do. Could make that kind of prettier, huh? Now, what am I doing between the next 2 bars? Between 0, that was from negative infinity to 0. Now from x equals 0 to x equals 2. What am I doing? Still decreasing. I'm decreasing all the way to 3. So I am certainly decreasing from 0 to 2, but I'm concave what? Concave down. So I have a point of inflection. I'm still going to decrease, but I'm going to be concave down all the way to the next break. And what happens at 2? I have another point of inflection. And then what am I doing between 2 and 3? Between 2 and 3, I am still decreasing, but after 2, I need to change to concave up. So still going down, but concave up to my next break, my next critical piece. Now, I stay concave up till infinity. But what happens up here after 3? After 3, I have a local, which we now know because of 4th degree behavior, it is an absolute minimum. I turn around and increase, but I must stay concave up. So I have a horizontal tangent. I increase forever, and I'm concave up forever. Okay? It is not the most attractive graph, but it's good enough. And more importantly, a grader can see what from your number line work that you were able to correspond negative infinity to 0, what was happening from both your first and second derivative. Decreasing, concave up. Between x and 2, between 0 and 2, decreasing, concave down. Between 2 and 3, still decreasing, but concave up. From 3 to infinity, increasing, concave up. Again, I can't give you coordinates, full coordinates of poi, but there are 2 points of inflection and an absolute min. The height of those points of inflection, the heights of any extrema are relative, right? You're not going to be graded on that, but you're going to be graded on where they are. It needs to be at x, the pois need to be at 0 and 2, and the local / absolute min needs to be at 3. Notice here where you had a horizontal tangent but no change in the first derivative, you do have a place of horizontal tangency, but it is related to a point of inflection rather than a max or a min. And how I know that without looking at the graph is because the derivative changed sign, did not change sign. In order for your graph to have an extrema, the tangent lines on the left have to change sign from the tangent lines on the right of that x value. If they don't change signs, the tangent lines on the left here of this horizontal tangent are negative, and past that horizontal tangent are still negative, no turning point. Okay, so I have a pretty freaking good picture of that x to the 4th, and I don't know what its equation is. So the handouts that are linked on our page do give you a nice little wrap up. You are, for the most part, now I'm going to erase this so I can, you really are drawing 4 pieces, unless you have no concavity in which you have a linear piece, or no increasing or decreasing, or which, in which case you have a horizontal piece. These are the only curves that you're drawing in between each one of your critical places, right? And I did this in a last video. Either you are increasing and concave up, or you are decreasing and concave up, increasing, concave down, decreasing, concave down. And those correspond with the signs of your derivative. If the first derivative is positive and the second derivative is positive, first derivative positive, increasing, concave up. First derivative negative means you're decreasing. Second derivative positive, concave up. First derivative positive, increasing. Second derivative negative, concave down. First derivative negative, second derivative negative. You do not have to write in these terms, but know that AP will. They'll say things like, given a differentiable function f, where f prime is greater than 0 on the interval 0 to 3, blah, blah, blah. They will write in this notation. You just have to know what it goes with. And then when you are asked to sketch a graph from derivative information, which we really did in a prior unit, it's just that now I can be more precise with you. You are drawing one of these four curves unless you are drawing something straight. And how do I know when I'm drawing something straight? Right? The first derivative, right? Second is constant, or the second derivative is constant. All right, so this is a handout that is also linked on the page, and we're going to go through this because the questions on here are really good. Now, you can see from the handout, there's questions 1 through 11. I'm not going to answer questions 1 through 11 directly. I'm going to just look at the graph. And just like the previous example, please note your labels. This is the graph of a derivative. How do I know? They labeled it such. I am not looking at the original, but they're asking me questions about the original. So given f prime, answer questions about f. And or sketch reasonably graph of f. All right, so again, I'm not paying attention to the questions just yet. Here's what I notice. I notice where the first derivative is equal to 0. I notice I have endpoints. I also notice where the first derivative is negative. Where should I put this? I guess over here. I'm going to make my first derivative suspect list. And my number line, I have closed circles at 0 and 8, and my first derivative is 0 at 3 and 6. My first derivative is negative from 0 to 3. My first derivative is also negative from 6 to 8. But the first derivative is positive from 3 to 6. Therefore, the graph I do not see is decreasing from 0 to 3, increasing from 3 to 6, and decreasing from 6 to 8. Further, look at this situation. I am going to use the graph of the first derivative to give me second derivative information. Okay? So, notice I don't care about endpoints because the second derivative talks about concavity, and I don't care about concavity. There's no concavity at endpoints. So, I want you now to think about this graph. I want you to think about the tangent lines on this graph. Remember, F double prime represents the slopes on the first derivative. So now look, forget about the colors. Just look at the graph of the first derivative and tell me about the slopes there. What is true about the slopes on F prime? Yes, the slopes on this graph, right? The second derivative describes the slopes on F prime. So where are the slopes on F prime equal to 0? The slopes on F prime are equal to 0 at those places. Therefore, on your number line, what is that, about 4.5? The second derivative is 0 where the first derivative has turning points. Right? So that was at 1, 2, 4.5, and 7. Now, talk to me about the slopes on this graph in between where they're equal to 0, right? What are the slopes here? The slopes on F prime are positive. The slopes on F prime are negative. The slopes on F prime are positive. The slopes on F prime are negative. The slopes on F prime are positive. Notice I'm going to put an intermediary step here on my number line. I'm not going to put F down there. I'm going to put F prime. When the derivative of F prime, is positive, F prime is increasing. Look at the graph and make sure that makes sense. This graph that I'm looking at, not the graph of F, the one I can't see, the graph that I'm looking at, isn't it increasing from 0 to 1 and increasing from 2 to 4.5 and increasing from 7 to 8? And isn't the graph of F prime decreasing from 1 to 2, and 4.5 to 7. But what does that say about the original? When the second derivative is positive, the first derivative is increasing, but the original is, oh gosh darn it, it's not going to let me write there, concave up. When the second derivative is negative, the first derivative is decreasing, and the original is concave down. When the second derivative is positive, the first derivative is increasing, and the original is concave up, and so on and so forth. And of course, I think if you can look at that and see that that is true. Oh no, sorry. The graph that you can't, F is the graph you can't see. So here's why I went through that so laboriously, slowly. If you have the graph of the derivative, the first derivative, you can use the first derivative for everything. Because f double prime is the slopes on f prime is equal to 0 when the first derivative has a max or a min. I should say extrema. Then your original, though, every time f prime changes from increasing to decreasing, the original changes from concave up to concave down. So you can use the graph of the first derivative without getting a second derivative. Because you might say to yourself here, how can I possibly draw the graph of f and answer anything about concavity when I don't have an equation for f prime? Unlike the first example I did, I gave you the equation of the first derivative so you could find the equation of the second. The only thing I gave you was the graph of f prime, and from the graph of f prime, you had to get all information about f to be able to graph it and answer questions on it. Crazy, right? So look at all this information, because I need to erase this because I'm going to draw on top of, because again, I'm going to go all the way to number 11 where it asked me to draw it. Then I'll go back and fill in the questions, okay? So number 11 says, given a point on the original, if they give you that, please graph it. Now they want me to graph the pieces in between. So here's what I'm going to do. I'm going to use those number lines that you took a picture of, right? And I'm going to draw my breaks. I mean, they're not really breaks, but breaks where I have to draw a different piece. Everywhere the first derivative has a turning point, or has an x-intercept. And endpoints. right? And then I'm going to draw one of those four pieces. So looking at the number lines that you hopefully took a picture of, I'm going to start at the right endpoint. And at the right endpoint, the first derivative is increasing, but negative. So what does that mean? F prime is negative, F double prime is positive because F is increasing, right? Slopes are positive. So what does that mean? Decreasing, concave up. So from start, decreasing, concave up. Check. In between 1 and 2, what's going on? First derivative is still negative, but what are your slopes? So you are decreasing, concave down. You changed concavity, you have a point of inflection. How about between 2 and 3? Between 2 and 3, first derivative is still negative, but what are the slopes on first derivative? Positive. So you are still decreasing, but concave up again. Over-exaggerate your concavity when you're doing this. I didn't do a good job at exaggerating my concavity. Point of inflection. Oh no, not point of inflection, right? The first derivative is 0, so I have a horizontal tangent. So there, f prime is equal to 0. But the slopes are still positive. So you're still concave up. And once you're past 3, the first derivative is now positive, and the second derivative is still positive. So you're increasing and concave up. But now, between 4 and 5, what's true? First derivative is positive, but the second derivative is negative. So you're still increasing, but concave down. What's true at x equals 6? Your first derivative is equal to 0, so you have a horizontal tangent. And I guess that's, oh yeah, that's 6. I didn't do a good job of drawing the purple line at 6, but there's 6. And what are the slopes on f prime? Between 6 and 7, your first derivative is now negative, and your slopes are negative. The slopes on f prime. So you are going to decrease and be concave down. Between 7 and 8, the first derivative is negative, but the second derivative is positive because the slopes are positive. F prime is increasing, so you are decreasing but concave up. Notice where the first derivative had an x-intercept, the graph you drew and changed from positive to negative or from negative to positive, the graph I drew had a local max. The graph I drew had a local min. I have a right endpoint, and for my right endpoint, the graph at the right endpoint the derivative, first derivative is negative right after it. Therefore, I am decreasing from the, right. The left endpoint I am decreasing from. So this is a local max. The right endpoint, the derivative is negative right before it. Therefore, I was decreasing to a right endpoint. And everywhere the derivative had a turning point, the graph I drew had a point of inflection. All right. So I'm not going to go through on the video and answer all 1 through 10, but we really have answered them already, right? Where is the original increasing? Where the first derivative is positive, where you're decreasing, where are your critical values, where your derivative is a 0 or do not exist, blah, blah, blah. Notice number 6 starts saying, where does F have a point of inflection? Your answer to that is where the first derivative changes direction. Now, 7, 8, 9, and 10 ask about absolute. Notice I only labeled these locals. So I'm going to erase all this. So pause it or take a picture or whatever. I guess it's a video. You can always go back, right? Boomer moment. 7, 8, 9, and 10 ask about local and absolute. So for instance, 7 says, where's the absolute max occur, but it closes an interval. By the extreme value theorem, you're going to have an absolute max on a continuous, right? And if F prime is, if you have a derivative everywhere on F, it means, right, since the derivative exists everywhere, F must be continuous everywhere on this interval. So if they chop us from 0 to 2, now look at the graph we just drew, but even without that, the first derivative is negative. F prime is negative on 0 to 2. Therefore, F is decreasing on 0 to 2. And if F is decreasing, the absolute max on that interval is at x equals 0. So 8 is asked for the absolute min, which would be at x equals 2. And then 9 and 10 just change the window you're looking at from 3 to 6. But notice what the derivative is always. On 3 to 6, the derivative is positive. Therefore, the original is always increasing on a closed interval. And if you're always increasing on that interval, then the left endpoint is the absolute min and the right endpoint is the absolute max. And you can look at the graph that we drew to verify that. Okay. All right, that is the end of this, there is another handout that I want you to practice with, but I purposely added this one because its label is different than the one we just did. Look at this label, right? Look at your labels. If they don't specifically draw a dot or an arrow there, I would have to accept answers either way, but I'm telling you now to put dots there. This is the graph of the original. So the questions on this handout ask you, given the original, answer questions about the derivative. The previous one was given the graph of the derivative, answer questions about the original. Okay, so given f prime, talk and graph about f, which again, we did before, we did in a previous unit. We're just able to do it with a little bit more precision now. And here, this really is old. Given f, answer questions and or graph f prime. All right. I will see you in our next live session.